Assalamu alaikum, hi everyone. This video lesson is related with my previous video entitled The Gauss-Jordan for Nodal Analysis with Matlab. So the Gauss-Jordan is categorized as the iterative method, and this video, on the other hand, will demonstrate the Matlab programming for a couple of direct methods, which are the Gauss elimination method and the Gauss-Jordan method. Most of the textbook normally begin with the direct methods, then followed by the iterative methods. But from my point of view, as far as the programming is concerned, the programming codes for the direct methods looks more tricky than the iterative methods. Okay, now let's begin with the programming. So these few lines coming from the nodal analysis, which are exactly the same with the Gauss-Jordan video, so I don't think that I need to explain anything here. And here again, matrix A and B resembles the simultaneous equation of the nodal analysis, so we can check right away the nodal voltages using Matlab inverse matrix, the built-in formula, such that like V Matlab equals to the inverse of A times B, and if we run till this line, Matlab gives this value as the result of the nodal voltages. Alright, from this point onwards, we intend to formulate the Gauss elimination method, the basic Gauss elimination method, and the modification of the Gauss elimination, which is known as the Gauss-Jordan method, to obtain the same results provided by the last line. So the very first step of the Gauss elimination is to merge matrices A and B to form the so-called the augmented matrix. Here we let P equals to the combination of A and then B. So let's put some comment here. So this is the original augmented matrix. Alright, so if we run till this line, we can see that matrix P here is exactly the combination of matrix A and B, in which P has 3 rows and 4 columns. To know the number of rows and columns of P, we can simply type N is for number of rows, M is for number of columns, equals to the size of P. Alright. So if I highlight this line and I right click and select evaluate selection, I get N equals to 3 and M equals to 4, of course. So our aim is to reduce matrix A, inside P here, meaning that the first 3 columns, to become an upper triangular matrix, such that this and these elements become zeros, and of course the values of other entries will change during the process. So the central equation that related to the row reduction formula is the equation, let's have some space here, and maybe some tab. So this is the main equation. Pi colon equals to Pi colon again minus Pij divided by Pjj times Pj colon. Okay, so Pi colon on the left hand side is the ith row of matrix P, and even this one. The difference is the left hand side is the updated value and the right hand side is the current value. And then minus this term if obviously the element, the ijth element of P, and then this is the elements of the main diagonal, you know, this, and this, which is known as the pivot. And finally, the last term is the jth row of P. Okay, so now we perform this operation for the first column and the second column of matrix P. So it is from the first until the n-1 column. Therefore we can write something like for j from I until n-1, you know, which means j equals to 1 until j equals to 2, and then we continue again with another for loop for I equals to 1 until n. Okay, so j corresponds to the column, I corresponds to the row, and here we only want to execute this operation for the elements below the main diagonal. So we put a condition. So do the following line if I is greater than j, and we put some tab here, and then n for the if, n for the inner for, and another n for the outer for. Okay, let's see what we have here. So after we run the program up to this line, you can see on the command window a matrix P evolves from its original to the, you know, and first this 0 and then this 2 becomes 0 and finally all these 3 become 0. So this is called the final form of P is called the reduced row echelon form, you know, in which you can refer this to the textbook. So basically this inner loop is to make all the elements below the main diagonal of the jth column to become 0. Or to check the value of P more properly, maybe perhaps we can write something like maybe here f prints f, and we write some statement like the augmented matrix after stage, let's put a variable here, is and then and enter here, comma j. So let me put some space here, and then p, and we can comment this line. Okay, even here maybe we can comment, and I think just comment B and A, so we don't need to display so many things on the command window. And if you run the whole things, so we get a more proper results. Okay, so just want to explain this. This is this part of string becomes like a variable in which the value of j will be substituted here. Okay. Okay, now we we rerun, maybe, but we already run, and then the remaining step in the Gauss elimination method is to perform the back substitution. Okay, obviously now we can get V3 equals to P34 divide with P33, you know, because now we can derive vector, you know, the last element in the nodal vector based on the last row of P. So this value times V3 equals to this value, meaning that if we take this, which is P34, divide with this, we get V3. And then we continue with V2. So finding V2 require the information of V3. So this equals to P24 minus P23 times V3, and divide the whole thing by P22, and finally V1 equals to P14 minus P12 times V2 minus P13 times V3, and divide the whole thing with P11. Okay, so these three equations resembles the back substitution. Okay, now we got the value of V. Okay, by the way, these whole lines, you know, can be written in a more compact manner, such as first maybe we can comment this, and then we define a vector and 3 by 1 for the nodal voltage, like V equals to 0s and 1, and then next we can write a while loop by starting with like k equals to n, and while k greater than 0. So we write Vk equals to, now we want to create a single equation, single formula that can represent every lines. So Vk equals to P K M, you know, so M equals to 4, of course, in this particular case, minus P K. Now we take the kth row of P, excluding the entry in the rightmost column. So we only take until n, and times with the vector V, and we divide everything with P K K. Sorry, semicolon. Or maybe we remove this first, and we write k equals to k minus 1, and the while loop is completed. All right. So if we run this, we get the same results. The vector v equals to this value. You know, you can compare with what Matlab has produced. And maybe if you want to put a semicolon there, so, and then again printf like we can write from back substitution of the Gauss elimination method, vector v is obtained as enter v. And let's run and see what we have here. Okay, so this is the result provided by the Gauss elimination method. Alright, now let me demonstrate very quickly how to modify the Gauss elimination method to have the Gauss-Jordan method. But before that, let's put some comments and text lines. Sorry, should be here. Maybe we can add something like print f. This is maybe this is the answer using Matlab inverse matrix. Okay. And what else? Maybe here we can put a partition. So this is Gauss elimination, and then we print f. Maybe we can put some enter and the breaking lines maybe, then put some text here like from here we are doing the Gauss elimination method, enter. Okay, and then perhaps you can copy these lines maybe, and then paste it down here and change this to Gauss-Jordan method. So from here we are doing the Gauss-Jordan. All right. Now it is Gauss-Jordan method. Firstly, let's clear some variables which are P and V that have been done in the Gauss elimination. So I think let's put it here. So clear the big P, V. Okay. And then we regenerate matrix P. So we write again P equals to AB. All right, then what? So we need to modify this for loop, okay, that perform the row reduction. So the difference between the Gauss-Jordan compared to the basic Gauss elimination is, in Gauss-Jordan, our aim is to reduce matrix A, you know, this matrix, inside P, to a diagonal matrix, meaning that all elements for A become 0 except this diagonal. So meaning that we want to make this 0, this one 0, and this one is also 0. Now, since the third column, you know, the nth column, which is the third column, also involves, we need to change this from j equals to 1 until n minus 1. We need to change it to from 1 to n, because this time even the third column should involve. So what else? And secondly, we need to change this if statement, because this time we want all elements of A except the diagonal to become 0. So we change this, instead of if 1 greater than j, we write if 1 is not equals to j, perform this following equation. And we don't need to change anything in this main equation. And let's run and see what we have until this point. Okay, now we can see that there is a diagonal matrix inside P, and the rest is easy. Now, since this reduced matrix A is a diagonal, we can solve any elements of vector V right away without the need of doing the back substitution. Thus, we can simply write like so maybe first we can copy this. First we generate or we introduce a zero vector for V, and then we write a for loop for k equals to 1 until n. Vk is, this time it is very straightforward. Vk, equals to this value in the rightmost column divided with the diagonal elements. So that will be V1. V2 is this value divided with this. V3, this value divided with this. So we can write Vk equals to Pk M, which corresponds to the elements in the rightmost column, which is column number 4, divided by Pkk, which is the elements of the diagonal 1, element 1, element 2, and element 3. And then that's all, I think, end. So let's rerun and see what we have. Yeah, because I put semicolon here, so the command window doesn't show the results, but we can write something like this, copy here and then paste it down here. So we say from this is not back substitution, this is actually the direct division, or we can write from the division by the diagonal or anything else you can write of Gauss-Jordan method. Vector V is obtained as V. Okay, and now let's run everything for the last time. And it is shown in the command window, the results produced by Gauss elimination, where is the here, and the Gauss-Jordan, this one, both of them agree with the results produced by the Matlab inverse function. So I think that's all for now. Thanks for watching.